Hi, I'm Dylan Taylor, Chairman and CEO of Voyager Space Holdings.
I'm Ken Eppins, founder and CEO of Orbit Guardians.
Hi, I'm Raphael Rodkin, founder of E2MC Space Ventures.
And I listen to the Cold Star Project.
And I listen to the Cold Star Project.
And I listen to the Cold Star Project.
This show is for entertainment purposes only and is not what is termed professional advice. The Cold Star Project is proudly presented by the Operational Excellence Society. Cold Star Tech is a supporter of the OPEX Society, and Jason Canigan is a member of its board of advisors. Talk with us at Cold Star Tech to find out what we can achieve together with your Lean Six Sigma or Operational Excellence programs. And check out opexsociety.org to learn more. Let me take this time to remind you that Cold Star Technologies is a promotional partner of the America's Future Series, which has events in person and online about national security, critical infrastructure issues, space industry, technology, things like that. And so if you're interested in the future of this nation, I hardly recommend you check that out, the America's Future Series. My guest today is Dr. Paul Van Susante. You may recall he was on before, and that was like 2 or 3 years ago. The numbering system for those keeping score of these episodes of the previous time was number 129, and this version was number 238, so it's been a little bit. Dr. Susante is an assistant professor at Michigan Technological University. He has a very cool background in civil engineering and also his master's degree and PhD in engineering systems coming up through the Colorado School of Mines, another great program that we've talked about on this program. So he has recently put together a number of really cool projects that I wanted to catch up with him on, some NASA challenges and grants and things like that. And also his own company, which you can find info about at huskyworks.space, and I'll link to that in the description below. So it's always fun. Paul's very technical, of course, and if you're interested in like in situ resource utilization, building stuff on the moon or on Mars, this is a conversation you really need to tune into. Listen up. Paul, welcome. So you won a number of grants through the last year or so since we last talked. I want folks to go back. I'm going to link to that previous discussion because we talked about like lunar regolith and everything that's weird and upside down about dealing with the moon. And so we're exploring more about what Paul's done over the last period. And he's gotten involved with a number of grants, NASA challenges. And that the first thing we're going to start with is called LuSTR, LUSTR, from 2020. So maybe it's been longer since we last talked. Let's begin with that. What was it, and what did you learn?
Thanks, Jason. It's great to be back on your show. It's always a pleasure. So LuSTR is the Lunar Surface Technology Research Grants. Those are specific academia-focused grants to develop technology. And the one we were awarded in 2020, seems a long time ago already, is specifically intended to study a technology to find and identify, quantify volatiles in the lunar regolith, as well as detect or measure really the geotechnical properties, so that we can then design our future excavation systems properly, basically. And so over the past 2 years, we've been very busy developing that technology. And so the technology that we proposed and were funded for was a cone penetrometer. And so a cone penetrometer works basically by hammering it in the ground. Think of a needle that you hammer on the ground, and the amount of resistance that you encounter going down tells you something about the geotechnical properties. And so it's used on Earth here in many different ways, but we modified it specifically for the lunar surface because things like certain membranes don't work on the moon. Things like water pressure, pore water pressure, again, doesn't work on the moon, so we needed to find something else. And so we instrumented our cone with a load cell at the bottom, so we could measure the load right at the tip of the cone, and that allows us to extract certain geotechnical parameters that you can't measure just from the impact loading. And then the other thing we did is we also included a heater in the cone section, not the tip itself, but right just above it. So we have a heater section and a couple of thermocouples there. And so while we hammer this cone down in the ground, we stop every 10 centimeters. We could go down 1 meter, so this would give you about 10 intervals roughly. And then we heat up that cone, or at least that cone section, and we measure the thermal profile. You know, just like you have boiling water stays at one temperature because there's a phase change happening. All right, it's the same kind of thing we expect to see in the ground, and we actually do see that, where you heat it up, and then depending on which volatile is present, you know, water is one, but there are things like carbon monoxide, methane, ethylene, all kinds of different things as well. And so each of those volatiles have a different phase change point. And so at which temperature we see a change in that thermal profile will allow us to identify which volatile was present there. And how long that phase change takes tells us how much of it is there, basically. And so that will allow us to measure, you know, at 10 centimeter intervals, which volatiles would be present there, if any, right? And so we get the geotechnical properties and the volatile measurements as well.
Okay, let's define volatile for people who are not familiar with I was going to say earth science, but that's these terms, right? You've got boron or something, a noble gas or something that doesn't do very much, right? And isn't very reactive. And then we've got things that do react very well.
Yeah, so the word volatile here, it means basically it becomes in a gas form under normal atmospheric conditions, essentially, right? And so most of those terms are based on kind of what our human experience is, because every material has a gas phase in a way. But in this case, the volatiles are designed to say that they're gas form under normal Earth conditions, if you will. And so they are not in gas form on the moon because it's so cold in those permanently shaded regions, and so they are stable for billions of years under those conditions, even though under vacuum normally they might evaporate, so to speak, but that doesn't happen because it's so cold. But because we then heat it, right, it goes to those phase transitions when we add energy to it, and then we can change the temperature, and that's what we measure with thermocouples.
Okay, and these are wonderful resources that could be used for who knows what, power supply and energy creation and things like that. So, okay, very, very useful. Do you think that they're going to be present in quantities that matter?
Some of them, yes. You know, some of the data that was gathered from, I forget the name of the impact mission. You'll have to look it up.
Yeah, okay.
Anyway, so a stage was impacted into the lunar surface, and the plume composition was measured. And in that plume, there were all these different volatiles that were measured that did not originate from the impactor, so they had to come from the lunar surface. And that includes water, but it also includes mercury, for one, which is a challenge, of course, to deal with. But also things like carbon monoxide, methane, and other kinds of volatiles, right? And so the percentages vary location to location, but they were definitely found in interesting quantities. So.
Okay, very good. So despite the moon being dead, it's full of building blocks that we could use. Okay, interesting. So how did that finish up? So you do the grant, I guess. Is it like a SBIR or an STTR? You apply for it, they screen, approve some. You have,
it's the same award process.
Okay.
Yes.
How do you know when you're done? I guess a certain time expires and you deliver a final report.
Essentially, yeah. So these are 2-year grants, $2 million. So it's a lot bigger than a SBIR. But the idea here is to get the technology level from like 2 or 3 to like 4 or 5, if you can. And so the final product is a technology upgrade, if you will, and that is presented or reported to NASA in the form of a final report. But of course, there's lots of hardware developed as well. And so in our case here, we are collaborating with Honeybee Robotics, and so they have built for us the Z stage, which basically modified Viper system, the Trident drill. And so instead of the drill, we are mounting our cone penetrometer on it. And so they've manufactured that for us. We are field testing it, so we're mounting it on a field rover, taking it out in the field, and doing the tests with it. And then in addition to our cone penetrometer, we also have ground penetrating radar on it.
Okay.
And the reason for that is because when you do your cone penetrometer test, you get spot tests only every once in a while,
Mhm.
right? And so we want to know what goes on in between those tests. And the ground penetrating radar measures basically in between, whether it's homogeneous, whether they're layering, or whether there's rocks and ice blocks in between. So you might get lucky in that spot, but it might be totally dry over here, or the other way around, where, oh, this spot's dry, but oh, look at all this ice over here, right? So we
That
we
sounds
want
like
to
a
combine
great
those.
instrument.
Mhm.
Yeah. Okay. So that's going to tell whether something's there or not. And then I guess there needs to be an extraction machine that comes along after to really pull that stuff out.
Yeah, I mean, when you think about the Earth process of starting a mine, right?
Mhm.
So if you happen to find one gold nugget, that doesn't make a mine, right? So that might have happened to wash down the stream, and you
Right.
have found the one nugget over there. But to make a mine, so to speak, you need to map what is there. And so not just map it, but you also have to then design a proper excavation and processing system, so you can then not only say, yes, it's there, but we can also economically extract it. All right. And so once you have that full plan, meaning you know where it is, how much there is, you know that you can get to it, and you have the technology, to then extract it, then whatever is there becomes what we call a reserve. And a reserve is something that you can essentially go to the bank with and say, look, we know this is here. We know we can extract it. Here's our plan. We'd like to get a bank loan, basically. Right? That's how it works on Earth. On space, I don't know that there's any space bankers as
Thing
such
like
where you
that.
could go to.
Yeah.
But anyway, for NASA, that would be really important, because if you're going to bet your future astronauts on it, that they can come back using your propellant that you mined, then you have to make sure that it is there, right?
Right.
That you can extract it. And so that's the whole reason that we need to map it properly, so that we know we can extract it.
Yeah. This is quite exciting because it means that, that's the in situ resource utilization thing, right? We don't, for those who are just new to this and just fell into this show by accident, this is the kind of thing where we don't have to fly stuff to the moon. Right? Some of it's there already. We have to get a basic infrastructure there to be able to extract these building blocks, but then we can use them, and it's a lot cheaper to do that after a while than it is to fly them out of our gravity well from Earth all the way to the moon and then use them there, right? And Paul knows this. It's like, yes, I know. Okay, awesome. So next thing that you did was something called the NASA Watts on the Moon Centennial Challenge, and this is phase 1. So what was this for? How was it carried out? What does it mean to win?
Yeah, so one of the things that we need on the moon to be able to do all these really cool and important things is power, right? Without power, nothing happens. You can't excavate, you can't run your life support systems, you can't do anything without power. And so the Watts on the Moon Challenge is specifically designed to develop technologies, and this isn't what Centennial Challenge means. It's open to anyone, right? Anyone can propose something to NASA, but because it's a competition, you don't get any money up front to do it, right? So you don't set a proposal, then you get money, and then you get to do the work. In this case, it is you do the work, you submit it, and then you might win some money, basically, right? So it's a competition as such. And so the What's on the Moon phase 1 had 3 different scenarios. NASA was looking at providing power to 3 different kinds of things. And so we submitted a proposal to scenario 2, which was in this case to connect 2 NASA pieces of infrastructure. 1, the power plant, and 2, in this case, the ice processing plant, right? So like we're just talking about ice. Let's say we can excavate it, but then it has to be processed and extracted and then be electrolyzed in hydrogen and oxygen to make rocket propellant. And, how do you get the power from where the sun shines to, in this case, where the ice processing plant would be in the permanently shaded region where the sun never shines? And so we came up with a vehicle that would be able to drive down into the PSRs, kind of like a spider in a way, deploying a cable behind it while it would be going, and then connect from the solar plant to, in this case, the ice processing plant. And so the innovation that we have here was that we were using a superconducting cable for in the really cold areas, because we are below the critical temperature to go to superconducting status of the cable, which means zero electrical resistance, basically. And that means no losses. And that means for many kilometers of cable, yet no losses. And that's a really big thing, because efficiency translates into mass savings, right? Because you need a really small cable, and that means less launch to lunar surface. And so that's we won that one. So we won the grand prize for that scenario. And now we're actually in phase 2, level 2. And so we passed level 1 as well. And so now they changed the phase 2, changed the scenarios in a way. So now you have to design the power transfer and storage component. And you have to build the hardware to test it in the vacuum chamber that is liquid nitrogen cooled to minus 196 degrees Celsius. And so, making PowerPoints is great, but now you got to build the real hardware and show in the real lunar conditions that it will work. And so we're very hard at work right now to do that.
Right. Okay. And as anybody who's studied science, as we get close to that 0 Kelvin, the motion goes down to nothing. Right. That's the same thing here. You want to be able to transfer this energy, and so you've got a thin cable that basically has no resistance, and can stand up to these cold temperatures. What about the regolith? It's so sharp, right? Does it just sit there doing nothing most of the time unless you disturb it? And so once you've laid the cable down, it's fine, and or is there a risk of like the insulator getting cut if that's what you're using?
Yeah, that's a great question. So the cable itself doesn't move, right? And so once the cable is in place, there is really no reason for the regolith to move. The only thing that we don't know enough about right now is the electrostatic behavior of the lunar dust. Because when you have a cable and you put power through it, it does create an electromagnetic field. And we don't really know how that will interact with any potential electrostatic behavior of the particles. And so they might be attracted to it and they might cover the cable, which would be bad. But, at the other way, they might repel it, and that might be good. So this is something that we need to study. And the challenge with that is that we don't really have the capability of studying that very well on Earth, because the lunar regolith is created and made in vacuum conditions, and it has broken electrobonds that are not refilled from atmospheric conditions, because there's no other molecules it can steal electrons from, basically. And so there are certain things that are very hard to simulate here on Earth, right? So I have regolith, and it's the same sharpness, and we test that in our vacuum chamber. We can make it cold to the liquid nitrogen temperatures. But that electrostatic component is very difficult to properly simulate. You'd have to make the regolith under vacuum conditions, and it can never touch any air or anything like that. So it's really challenging to model that aspect of it.
Yeah. Even with the lab that you've created, there's still this big question mark element. And I'm wondering, like, if you get that cable that's the zero resistance cable, can you put another one around it or something that will create a magnetic field with the right polarity? Once does it attract or repel, right? I'm just wondering about that. When I got out of college, way back in 1997, my first job was in the power generation industry. I sold industrial gas turbine generator sets and diesel gen sets, and after a couple of years got into motor control centers and larger, designing other things like that. And so when you say, okay, we've got the power, it comes down the cable, and now we've got to figure out like what to do, how do we store and distribute this, right? I'm like, okay. So is it going to get pulled directly, or does it go to a battery that needs to be shielded somehow and then get pulled from the battery, which would be the most straightforward thing that I can think of?
Right. Well, so there are two aspects to this. One, the power generation is not a constant. Power generation occurs in the sun-lit regions, and it is only available during certain time of a lunar day, which is a month, basically, day
Right.
and night. And so NASA has given us specifications to say, look, we can generate power here for, I don't know, 8 hours, let's say, and then there's nothing for 12 hours, and then there's another certain number of hours where there's power available. So you can only we only supply a certain amount of power, and I think it was up to 10 kilowatts. That's kind of the power generation we're looking at. And then on the other end, we have the load, right? So this is a plant or something that is continuously 24/7 doing activities. And so that is the NASA load. And so we have to design the system in between the two that transfers the power when it's available up there, and then stores enough that when there's no power available here, we can still supply the load with enough power that it can keep functioning.
And
So,
and
yes,
if the
we
load
do
is
batteries for
continuous,
that.
you have to use some division.
Right. Well, it's
I got
it's
this
not
much to
entirely
work with, but I got to
continuous.
chop it up over 20 hours or whatever,
Right.
you know. Yeah. Huh. Okay. And that doesn't leave you many watts, does it?
Well, fortunately, because of our cable efficiency, I think the system is only like 2 kilowatts or something like that.
Okay.
So it's not, we don't need the full power that is
Nice.
supplied on the NASA side to be able to supply enough power to the NASA assets in this case.
Okay. And as time goes on, you could set up more of these and pull in more power. Interesting. Okay. So, and that now you're on phase 2, figuring out that distribution and storage. How long does that go on for?
So we just submitted our report earlier this month, and so this is about 2/3 through the phase 2 piece, or I should say phase 2 level 2, because there's 3 levels to phase 2.
Okay.
We've passed level 1, which was the paper design. Now we're been selected to do level 2, one of 7 finalist teams, or 7 semi-finalists, I guess. We each got $200,000 to start building the hardware and do these tests. And then in April, NASA is planning to come visit us here and observe us doing these tests and provide evidence that, yes, indeed, the system as we test it, indeed, performs the way we claim it does in the reports. And then, and then the assuming that, let's say we would pass, then in July, we would find out if we would be selected as one of 4 teams that would go on to level 3.
Okay.
And so we'd get another $400,000 at that point. And then level 3 is to actually test your full system, your full size system in a NASA facility.
Okay. They're still going to have some of the same problems, though, like the polarity thing, not having perfect lunar regolith to play with. But because some of the stuff you're not going to know until you actually install it.
We're proposing or hoping to propose an actual demonstration mission to the lunar surface where we could actually test this on a small scale to see that if indeed we get the performance that we're seeing or hoping to get.
Yeah, it's so fascinating that just once again, the stuff that we take for granted and know how it works on Earth becomes this big challenge trying to make it work on the lunar surface. Okay. Well, great. Well, I hope you get through to stage 3. It's a technology that sounds necessary to me. I mean, we have to be able to do it if we're going to get at that ice. And strategically, I feel that that's going to become more and more important, right? To be able to get there and claim the spot and get those resources and sort of
There's
set
a
up
limited
shop.
amount of those spots.
Okay. Third, we've got the NASA Break the Ice Centennial Challenge, and you did phase 1 of that. Let's talk about that. Again, similar format, right? Hey, pony up your own resources to get started, and if you do a good enough job, maybe we'll fund you a bit. What was this one all about?
So Break the Ice, like the title says, it's about mining the ice, right? In this case, so we've been working on finding the ice. Now we've been working on power supply, and then this component is about actually excavating and getting the ice out of the ground and delivering it to a ice processing plant. And so phase 1 was a design study where you were supposed to design a vehicle or multiple vehicles that would do that. And so the goal was to mine 10,000 kilograms of ice in 1 year to deliver 10,000 kilograms of ice to the NASA's ice plant, processing plant. And so they had, basically given you a scenario like our landing site is here, our ice mining plant is over here, or sorry, ice processing plant is over here, and our excavation zone is down here. And you had to design the vehicles that could go down into the mining zone, extract it, and there was a specific layering given to us by NASA, which is an assumption because we don't exactly know what's there. So they said that 20 centimeters is completely dry, there's no ice in it. Then underneath we have 80 centimeters of 4% ice, and below that there is 10% ice. And so within those parameters, you had to design your system. And so we designed a set of 5 vehicles, 2 different types, that would drive down, do the excavation, bring it to the ice mining or ice extraction plant. And then we had 2 vehicles that would then transport the ice from the ice extraction plant to the landing site, where it then could be electrolyzed into hydrogen and oxygen. And so with that setup, we got a runner-up prize. So we didn't win one of the top prizes, but we were one of 10 runner-ups. And so that was level 1. So a paper design study, we had to create an animation and all that sort of stuff. That was fun to do. But then now level 2, which is where we are at. So phase 2, level 1 was now a modification of that, where we had to design a system to simulate this on Earth. And so the goal here is to excavate cemented material. So instead of the loose regolith, the real cement powder-like material, we now have to excavate what they call controlled low-strength material, which is in a way really weak concrete. It's like you can stab a pen in it and it would break. Basically, it's not that strong, but it is still cemented, so it is not loose powder. And we have to excavate 12,000 kilograms of that material in 15 days.
Okay, that's much faster than the ice.
Yeah. Well, the other part is that you need to do it nonstop. So you need to do this as a demo. And so level 1 was to design that, and we have now been again selected to be in level 2 of this phase 2 competition. And so we got again some prize money for that. So in this case, it was divided equally among all the 13 US teams. So each team got, I think it was $38,000 and some change, which, by the way, does not cover all the costs. But anyway, so our robot that we're designing is about 250 kilograms, give or take, and it is going to do this task in 15 days to excavate 12,000 kilograms. And between the excavation zone and the dumping zone, you have to drive 500 meters each way in lunar terrain. And so we're going to drive over lunar regolith simulant instead of just some sand somewhere, actual lunar simulant. Because one of the driving factors of this competition is to study the wear on the systems.
Which is tough because the regolith is sharp.
Exactly. And it is really hard to simulate because regular sand behaves very differently than lunar regolith. And so we have, fortunately, 25,000 kilograms of lunar simulant. And so we can make it track. Unfortunately, not the whole 500 meters.
Right.
So we're going to have to do a bunch of laps. And then, we go to the excavation zone, we excavate that material, and then we go to do the laps back again and then dump our material. And we got to do that 3 times a day for 15 days. And then if all goes well, we will have excavated 12,000 kilograms.
Okay. Yikes. That's a lot. And it's a hurdle that we're going to have to overcome. Hopefully we could set the facilities closer to each other, but who knows? I'm not sure what the requirements are and what the minimum spacing needs to be, but again, necessary, important. Are you partnering with any other universities or organizations with these grant applications or contests that you're entering, or is it all Michigan?
Well, no. We like to think we can do everything, but no, we definitely partner with quite a few institutions, but also commercial companies and government organizations sometimes, depending on what is allowed within the rules and everything like that. So I've already mentioned Honeybee Robotics on some of the grants. For some of the other grants, we've partnered with other universities like University of Central Florida, University of Notre Dame, Colorado School of Mines, kind of, the usual suspects, if you will, in space resource work, but also with various other companies. And so we recognized that there's lots of Earth expertise here. And so we don't really want to reinvent everything totally from scratch. And so we would like to look at these other companies, see what expertise they have, and of course, whether they have interest or not to partner with us in maybe employing some of their technologies for Earth, and in this case, maybe in a modified version, apply them on the moon in the future, perhaps. And so several companies we work with there. One of them that we work with is Vermeer. Another one we work with is SIL, which is a battery manufacturer, or well, they do more than batteries, but we work with them for the batteries.
Had Edmund on my show, so yeah.
Oh, great.
Yeah.
And then MetOx is another company, in this case for superconducting cable, that we work with. And so there are several different size and types of companies and organizations that we partner with, because in the end, it's a team effort, and so nobody can really do this all on their own. Oh, and other companies they're forgetting is Lunar Outpost is another important one that we partner with. Formerly Maston, so now Astrobotic, we partner with them as well. So we partner with several different types of companies and partners there.
Very, very cool. Those partnerships are so important. Like you say, this is not a one-stop shop kind of world, right? Space is it's one of the things that I loved about it from the very beginning is it's very collegiate, it's very friendly. It's not like other universities where people are trying to keep secrets and shut the walls down and that kind of thing. It's much more friendly. You are working on a couple of other projects, landing pad construction and site preparation. Let's talk about what you're doing in those areas and why that's important, because I think folks who are new to this topic really need to understand, like, when you land a rocket, what happens. I'll let you explain that and why you have to do something to deal with it.
Yeah, that's a great question. So one of the challenges when you go to the lunar surface is that there's no atmosphere on the moon, and so the only way that we can slow down enough is retropropulsion, right? So you need to have a propulsive landing. And essentially, you need a rocket to slow you down, and then just before touchdown, slow you down enough that you don't crash, but land nicely on the surface. And that rocket plume for the rocket engine interacts with the lunar surface. Now, the lunar surface is made out of these really tiny, sharp glass-like particles down to 1 micron size. And the rocket exhaust plume, can go in multiple kilometers per second velocities. And so those particles get blown away essentially by those exhaust gases. Normally there's no wind on the moon, but these exhaust gases come out and take away those particles and blow them all over the place. Literally the entire moon gets covered, with these different impacts. As a matter of fact, the particles can go so fast, and one of my colleagues, Dr. Phil Metzger, has done a lot of modeling and research in this area, that some of these particles can even reach up to out of lunar orbit and reach the gateway in sometimes. And so if you time it wrong, then that amount of particles can actually hit the gateway as well. Now, by that time, they're not going necessarily very fast, and so there's not necessarily a lot of, let's say, micrometeorite impact, but there is contamination of those particles on things like solar panels and seals and things like that. So something we still would like to avoid if at all possible. Now, the closer you get, of course, the higher those velocities are. And, imagine, you have your nice solar panels and then you just go sandblast them with 3 kilometers per second particles, glass particles. That would not be very good for your solar panels, right? And so in this case, any infrastructure that we have on the moon that we need to survive there would get damaged by those exhaust plume induced particle flows. And that's something that we really need to avoid.
Mm.
Now, there are several ways people have studied in doing this. I don't think we have the answer quite yet, but there's quite a few different approaches to it. And so the key here is we need to have a surface that avoids that blowing dust, essentially, right? And so people have also looked at, building more of an enclosed space where prevent the plume from also expanding in general.
Yeah.
But each of these have their pros and cons as far as mass and how complicated is it to build it. But the first priority, right, even from one of the first missions on, is we need that hardened surface where there's no loose dust that can be blown away, basically. And so that is very important. And so the question is, how do you build that? So one of the projects I'm involved with, it's led by the Colorado School of Mines, is an autonomous landing pad site preparation machine in this case. So we're not actually building the landing pad itself, but we are preparing the surface to build the landing pad, right? Making it smooth, making sure it's nicely compacted so you don't get any uneven settlements in there. If there's a crater, we fill it up. If there's a rock, we'll remove it, right? So it needs to be a nice, smooth surface so we can then build the actual landing pad on top of that.
Okay.
Right. So that would be stage
Very interesting. And as an operations management guy, I'm extremely concerned with the order in which things are done. And when I start thinking about this, it explains why there needs to be distances between things, because the first rocket you bring down, or even if you just drop something from orbit and do what they did on Mars with the balloons that expand and it bounces and stuff, you're still going to throw a whole bunch of stuff up in the air, right, in that area. And then whatever you land needs to get away from there and go do that site prep somewhere else, right? But not too far away. Far enough, but not too far, right? And then the next lander can come down on that. And then you can start setting stuff up, because like you said, you don't want things getting sandblasted by glass crystals.
And one of the constraints, actually, and it's something that you might not think about directly, is that it's actually determined by when we do land with humans, hopefully in 2025. One of the criteria is that whatever we do needs to be within walking distance for the astronauts, in case the vehicle doesn't work for some reason, right? And so you have to be able to reach the lunar base, the habitat, from the landing location just by walking. And there's limited distance that they can have it, so you can't put it 10 kilometers away. That'd be quite the hike. So anyway, so there's many different constraints in the site location, the site choice of the landing pad relative to the habitat and the mining and things like that. But one thing that is really nice, because it is a vacuum, any dust you kick up on the surface by driving or mining actually stays very local, because there is no air for these particles to float in. Like on Earth, you get the wind blowing these particles over the place. That does not happen on the moon. And so as long as you, made of a defender or something, really contain the flow of these particles, they don't float if you kick them up. They just straightly fall down. So even if they're just 1 micron big, they will just fall straight down. And so if you limit the energy that you put in, right, by excavating, by driving, even kicking the dust, it will just straightly fall down, and it will not float way further beyond where you generated it. And so you can have things relatively close together from that perspective, but not with the landing site.
Okay.
That is the only time where you really kick things all over the moon, literally.
Yeah. And out. Like you said, I think it was you last time. I want to remind our listeners, or they may have never heard this. The gaskets on the astronauts' spacesuits only hold up for maybe 4 spacewalks or something, or moonwalks or something, before they get chewed up. And so that is going to be a limit on the walking as well, like we talked about.
Well, the spacesuits are being redesigned right now, right? And so
go Paragon.
Back in the day, we didn't really know about that, and so the spacesuits were not really designed to handle the lunar dust as such. So I'm sure they will last a lot longer now, but back in the Apollo days, those seals were degraded by 80% after 3 EVAs, so 3 days. So that's not good enough for any kind of operation, right? And so we want to operate these excavation vehicles for years, hopefully without any maintenance.
Mhm.
And so one of the key items is that wear and characterizing. And so one of the things we actually did in our vacuum chamber is we built a wear test where we can test materials under lunar conditions and see how they wear when they are exposed to
Right.
lunar dust, over long periods of time. And so it's quite interesting to see what happens when you expose the material samples to lunar dust over time.
Mhm. Yeah. Well, Paul, who do you want to hear from? Who do you want to connect with, and how can they reach out to you?
Well, we're of course interested in partnering with anybody that's interested in working with us. Well, there's two aspects here. One, we'd love to help anybody develop their technology. So we're not a company, so we're not developing a specific product ourselves to sell or anything like that. We are developing technology to help make this happen. But again, we're not selling it. We're a university. So part of what we do is generate the next generation that knows and is familiar with these kinds of things, so that A, you can hire them, and B, they're knowledgeable now, so that we can actually get to the next step. But the second part of that is we have test facilities here. And if you're interested in testing your lunar technology under lunar conditions, and if they're small enough to fit in our vacuum chamber, then we're more than happy to test your stuff here. And our facility, our vacuum chamber is roughly 1.5 meters wide, 1.5 meters tall by 2 meters long. So it's not a huge chamber, but it is big enough for CLIPS payloads, typically. That's what it was designed for, basically. And so we can put lunar simulant on the floor. We can interact with that, excavate it, do things with it, expose mechanisms to lunar dust. We can create a vacuum, 10 to the -6 torr roughly, and we can cool it with liquid nitrogen to -196 Celsius and heat it up to +150 Celsius as well. So we do thermal tests, wear tests, dust exposure tests, just simply, how does this thing behave under all these conditions, thermal tests as well. So all of these kinds of things we can do here. And so we work with partners on all of these things, technology development. We have a lot of experience moving regolith around and how it behaves. And, we compare how it behaves in atmospheric conditions versus how it behaves under vacuum conditions. And it's actually quite different in many ways. And so we found some pretty surprising things sometimes where it behaves totally intuitively. And so when you think it behaves one way, it really doesn't. And so it's we have a bunch of this knowledge built up now, and so we're of course writing papers to publish a bunch of this stuff. But we're willing to help anybody understand this and learn from all those lessons that we've learned in the meantime as well.
Right. Well, Doctor, is it through LinkedIn or email or another way that they should get a hold of you?
LinkedIn and email are typically the most common ones, and
smoke signals.
Yeah, well, it's kind of cloudy here, so I have a hard time seeing them. But any way that you can get a hold of me. huskyworks.com is the website. You can find contact information as well as project descriptions there. So that's another way you could get a hold of me.
I'll link to that in the description. Well, excellent. Thank you for doing this. I will link to our past discussion in the description below as well. If you're interested in what Paul was saying just at the end there about like stuff not working the way you would expect. I like to joke imagine you're a 5-year-old kid wanting to dig a hole in the backyard on Earth. It just throw everything out the window. that your experience of that would be like in terms of how the dirt behaves, what happens to the shovel, what happens to you, right? It's just all different. And I think we went over that in some detail in the past discussion, but appreciate you doing this, and look forward to hearing more about successes from you and the advancement of TRLs in this field going forward.
Thank you, Jason. I hope we have more good news to share in the coming months for proposals selected and competitions going on to the next level and things like that. So in the meantime, we're having lots of fun doing this. So thanks for having me.
All right, that was great, wasn't it? Thank you, Dr. Susante, for joining us. If you want to catch up with Paul, you can connect with him on LinkedIn or through his website at huskyworks.space. I want to remind you about the Operational Excellence Society, which you can learn about at opexsociety.org. and also America's Future Series. I think you should check that out if you're at all interested in national security and critical infrastructure, space technology issues. Now, the very last thing before I get out of here, if you are running a space or defense firm and you're a department manager or company president and you have got too much on your plate, if you've got a to-do list as long as your arm and you've got items on it, we need to get to this stuff, but you just never seem to get to. Month after month goes by and you never get to it. It's not going to happen by itself. It's not going to take care of itself. If you want some help looking at that, reach out to us through coldstartech.com or connect with me, Jason Canigan, on LinkedIn, and let's have a discussion about it. And I'd like to take some of that stress off of your plate. All right, join me next time. Thanks for being here. I appreciate you.